Very good morning. So we have covered certain portions of linear algebra yesterday, and we'll take over from there. And today, I guess he's going to start that assimilation part. So welcome, and we can begin your lecture. Thank you so much.
Good morning. I've been assigned a total of 8 lectures. One was a quick preview of linear vector space. Today was supposed to be a second talk on linear algebra, but instead of trying to list all the rules and formulas from linear algebra, I thought I will integrate the parts of linear algebra that is needed in doing data assimilation so that you can see the linear algebra in action instead of looking at it from the simple linear algebraic perspective. Secondly, I also want to talk about the plan for the rest of these 7 lectures starting this morning. How many of you have heard of 3D war? How many of you have heard of 4D war? How many of you have heard of Kalman filters? Okay. These are the basic tools. Anything else that came was built on the top of this. Ensemble Kalman filter, particle filters, 4D war ensemble. So once you know how to make the basic vegetables for eating, and once you master your basic cooking, then you can combine. In Kerala, there is a famous dish called avial. It contains every vegetable that you can find on the planet Earth. So the word avial is something, there's a mix. So if you know the basic ingredients, you can mix and match any way you want. All of it, please? So the emphasis must be on basics. So I'm going to start with the foundations of 3D war, then foundations of 4D war, the basic derivations and results relating to Kalman filters. All this we will do within the context of high-dimensional data assimilation problem. All of you? I also want you to know that I have given a set of 40 lectures in NPTEL. How many of you know that? Yes. That we gave quite some time ago, all the basic forms. We'll give you the references to that. In these 8 lectures, I'm going to be borrowing material from that set of 40 lectures. And those 40 lectures are based on the book that we wrote on dynamic data assimilation, and that was published in 2006, one of the early books that was published in Cambridge University Press. And we have been adding on to that, and we will address the question of when you have too much observation, how to pick. We will address all those questions. So please be attentive. Please bring your questions. We would like to be able to discuss. I think Wednesday evening, there is a session called hands-on. Depending on how it goes, we can do some problems. I don't know whether you want to spend your time programming sitting in here. Programming is something you need to do when you are probably all by yourself. So in consultation with Dr. Govindan Kutty, we will decide what we are going to do during the practicum session. That's a hands-on practicum session. We will adapt to that. So I'm going to start with a very simple basic model. So what are the basic players in data assimilation? Model. Model has unknown parameters. A model may have unknown initial condition. The model may have unknown boundary condition. Then data. The data relates to the process being observed. The model is a mathematical representation of the process that is being observed. If the model is good, the information from the observation must be useful to estimate the unknown parameter of the model. So model, parameterization, observation, and bringing the observations and the model together in marriage to estimate the unknowns, and that is data assimilation. I'm not a modeler. I'm not a physicist dealing with observation. My interests are in applied mathematics. I deal with conducting the marriage between model and observation. That is data assimilation. That is applied mathematical in nature. All of you? So that's how you have to separate your thought processes. So models. Model comes in various shapes and forms. At the topmost level, model can be divided into two groups: static model, dynamic model. In a static model, the unknown parameters are constant. In a dynamic model, the states of the model may be evolving. So I would like to be able to start with static model and talk about all the ways in which data assimilation can be looked at within the static context. After having gained some traction, we will then move over to dynamic models. Then model can also be classified into deterministic model and stochastic model. So static, dynamic, deterministic, stochastic. So you have four combinations: static deterministic, static stochastic, dynamic deterministic, dynamic stochastic. Almost all the models in all of sciences can be divided into one of these four groups. So I'm going to start with static deterministic model. So what is the idea? I'm going to pose a problem and try to develop a model, and we will build a model. We are not going to take somebody else's model to build a model and then start working on that. My favorite example, the example of a particle moving in a straight line at a constant velocity. Suppose there is a point z0, that is a starting point, and the particle is moving on a straight line with a constant velocity v. I don't know where it started. I don't know what is the velocity. But when applying the basic physics, I do know the position at time t must be equal to z0 plus vt. The distance traveled in time t, traveling at a constant velocity, starting at the point z0, zt is equal to z0 plus vt. So this is the mathematical model that represents the motion of a particle moving in a straight line at a constant velocity. I can complicate this model. I'm having a particle starting at a point z0. The initial velocity is u. There's a constant acceleration a. I can measure the distance is equal to ut plus half at square. Is my place? So in here, there are two unknowns, z0 and v. In the other problem, where the constant acceleration, there are three variables: z0, the initial velocity u, and the acceleration a. My job is to be able to describe the motion of the particle by a succinct mathematical model. I fall back on physics and got this model. I want to be able to estimate v0, z0 and v. In India, we say Z, right? There they say Z. So when I went to the United States, I used to say Z, Z, Z. Then they thought that I came from Timbuktu. I come to India, I say Z, Z, Z. Oh God, where did he go to all these days? Are you all in my place? It's like the thing I talked about yesterday. So there are few things in India we do. When I go, you then see, gee, we do things differently, right? So when I say certain things, I just want you to be reflective of what I do. So Z0 and V. So this is the model. This model is static. This model is deterministic. To be able to estimate the unknowns, I need observation. The observation cannot be unrelated to the process that the model is going to capture. So I'm going to now align people along the path so I have set young people and their positions are Z1, Z2, Zm. So I have asked people at these distances, and what is the job? Please mark your clock when the particle crosses you. So the particle is going to cross position Z1 at time t1, position Z2 at time t2, position Zm at time tm. So I'm going to have a table of values, data, T, Z. So T1, Z1, T2, Z2, Tm. Z. So I conducted the experiment, I collected the data. Data and observation are used interchangeably. I'm also going to assume that I can measure the position and time precisely. But you know, can I measure time precisely? Never. Up to a millisecond, up to a microsecond, up to a nanosecond. Are you with me? So I'm going to make certain assumption now. My observations of time and positions are exact. Why? I want to give all good things in my life. I don't want to worry too much about other nuances that come into play. Sir, you are sitting in the back. Can you see? Come on, I have a reserve for you. Seat here. Come on, come on. I don't want you to be sitting at the back. So I have the model, I have the data. I want to be able to bring the model and the data together. I would like to be able to use this data on this model, combine them to be able to estimate the problem. This is the prototypical in data assimilation. And this is not something you don't know. How many of you are physics students? What is the first experiment you do in physics class? To estimate the acceleration due to gravity. What did you do? There's a pendulum, there's a string, they give you a stopwatch, you hang it, pull it, 10 times, you count the total time. Change the length 10 times, you count the total time. 10 times, count the changing the total time. You plot. Then based on the slope, you know the length, you know the time, you estimate the acceleration due to gravity. Are you all with me, please? That's an estimation problem. That's a data assimilation problem. You are conducting an experiment. So what is the mathematical formula? T is equal to 2 pi square root of 1 over L by G. L is known, G is not known, T is known. The knowns and unknowns. There is data, there is mathematical expression that you do. So you already know what data assimilation is. That's a static data assimilation problem to estimate the acceleration due to gravity. Almost all the experiments you do in the physics lab, I want to be able to determine the specific heat of water. Have you done that experiment? I am a physics student. My bachelor's is in physics. Everybody please? The latent heat of ice, the latent heat of steam. These are all standard problems that you do in the laboratory in a physics class. Nothing different from that. So I want you to know that data assimilation is not something new. You may not have heard it in the context of data assimilation. It's a new name for an old problem. So data assimilation in this context is primarily used to represent the problem of estimation. There is another concept related to this, is called inverse problem. I will come to that a little later, but let's proceed with this problem. So what is it I want? I want to be able to use this in here to get what I want. So ZTI, according to this, ZT1 must be equal to Z0 plus VT1, ZT2 is equal to Z0 plus VT2, all the way up to ZTM is equal to Z0 plus VTM. So I have plugged in the data into my model. I got YAM equations. What is YAM? I don't know. Generally, it's large. When you do the simple pendulum, you cannot measure exactly the time of oscillation for one oscillation. So what do? You do 10 oscillations, take the average. Are you all with me? Come on, guys. Is there a non-physics student in this class? Is there somebody who has not done physics? Come on, please raise your hand. I want feedback. It's not a crime. Please understand. So I simply want to know whether you have done experiments of this type when you were in college. That's all. Now, what is that I want to do? So this is the actual positions observed. This is the model predicted positions. So this is model predicted. This is actual. Actual. I don't know what Z0 is. I don't know what V is. The difference. So what is it I would like to make? I would like to make each of these equality to be true. I don't know how to pick Z0 and V that will render this to be inequality. So to do that, what am I going to do? I'm going to compute the difference between the two. And I'm going to call this as errors, ET1, ET2, ETM. So let's talk about this. What is this? This is the error. So using the model, I can predict. I have the actual observation. The difference between the actual observation and the model prediction is the error in prediction. My job is to be able to control this error. This error can be positive or negative, but the square of the error is always positive. So I'm going to construct a cost function I'm going to call C a vector, which is Z0, and V, that is unknown vector, that belongs to R2. Instead of calling it C, I'm going to rename it as X. So let X be the unknown vector Z0 and V, that's a two-dimensional vector. I'm now going to define a cost function J of X. And what is J of X? My J of X is equal to ZTI minus Z0 plus VTI whole square summation I is equal to 1 to I. This is simply equal to summation E Ti square I is equal to 1 to I. So this is what's called sum of squared error. So it's a cost function. Sometimes we call it objective function. The objective function is the sum of squared error. Please understand, if I expand this, I know ZTI, I know Ti, so it's a function of Z0 and Ti. It occurs as a square, so it's a quadratic function in the components of the unknown vector X. It's a quadratic function in the component of the vector X. All of you with me? So how do I state my problem? My problem is stated as follows. Minimize J of X with respect to X belonging to R2. All of you? Keep nodding your head. Say it again. I have a hearing loss in my left ear, so sometimes I'm not able to hear very well. Or could you? I just want to understand cost function for one. Cost function is a function of the unknown. I want to minimize. So look at this now. I want to maximize my profit. I want to minimize my loss. The error can be thought of as a loss. It can be thought of as an objective function. It can be thought of as a cost function. My objective function in economics is to maximize your profit. Objective function in engineering is to minimize the total cost of production. Maximize the profit. Are you in my place? So cost function, objective function, criterion function, they are all common words that are used to denote the goal. The goal is to find the unknown Z0 and V for which that will be minimum. Got it? Yeah. Yeah.
Now you mentioned just now that I want to maximize, or I want to find the optimal value.
Yeah.
So how did you arrive that we want
Good.
to find
Optimum means maximum or minimum.
Yes.
That's right. So I want to, error is something I don't want.
Okay, yeah.
Got it?
Yes.
If it's a gain, I want more. If it's a loss, I want less. Error is a loss. Error is a cost. So I'm going to take this as a minimization problem. Now look at this now. The problem is one of estimation. The problem is estimation of parameters in a static model. We convert that problem into one of minimizing a cost function, objective function, which is the sum of squared error criteria. Why? Anything we want to do in engineering, anything we want to do in science, we want the solution to be best. Are you with me, please? Now let's talk about that now. I don't know how many of you are married. Don't tell. So when you are searching for your spouse, either party, you want the best person to be your life partner, right? But do you do a test for a life partner? If you do a test and want to find a global solution, you will never be married. Are you with me? After wedding, the wife says, my husband is the best husband. The husband says, my wife is the best wife. But did they do a global search? Come on, guys. You do a local search and get married and be happy. But here, no local marriage. I want a global solution. I want a truly optimal solution. I want to look everywhere. Where to look? Where is everywhere? My X can be in any place in the two-dimensional plane, R2. So this is called unconstrained optimization. I can go anywhere to find my partner. That's not what we do in life, but that's what we want to do in my problem. So this is an example of an unconstrained minimization problem. Minimization problem in 2D. If you are to minimize with respect to one variable, that's called univariate optimization. If you have to minimize with respect to multiple variables, that's called multivariate optimization. To do univariate minimization, you need univariate calculus. To do multivariate minimization, you need multivariate calculus. You remember? Linear algebra, multivariate calculus, probability, statistics. These are all the prerequisites. Now you know why. Don't believe me, that's what you need. That's what you need. Is the problem formulation clear to all of you? Okay, good. I'm going to keep giving homeworks. So I'm going to give you a homework by converting it to a univariate problem, but in the class I'm going to solve it as a multivariate problem. So how do you solve this is a univariate problem? So the univariate approach. In the univariate minimization, what is that you do? You compute the gradient, equate the gradient to 0. You compute the second derivative. At the minimum, the second derivative must be positive. How many of you remember that? Come on, guys. That's right. That's right. You have done it. How many of you have a calculus book with you? In India, what is the culture? I'm an Indian product. So when I say this, it is not your criticism. I'm including me. In India, what's the culture? You buy books, you spend the semester, finish the semester, sell the books. Your table is clean. When you graduate, you don't have any textbook with you.
Yes, sir. For maximum value, second derivative.
No, I'm talking about other problem. I will come to that. But when you go to work for an industry, which you'll soon be, where will you go? You have to develop your own personal library. So please, a pizza costs you $500 rupees, right? You can buy good books for 300 rupees. Build your library. Get a good book on calculus. Get a good book on probability theory. Get a good book on statistics. You get a good book on optimization. Get a couple of good books on programming. Those are going to be your friends for life. Are you with me? You'll all be working at least until when you are 65 years old. Many of you are in your mid-20s, perhaps. You all look so young. I used to look that young once upon a time. So you have 45 years of productive academic, some life in front of you. Are you with me, please? That's right. Hey, I have been working since 1973. I'm not done yet. Are you all with me? So build your library so that you can fall back to learn from. Good. Now let's go to the problem. So what is the first thing? I need to be able to compute the first derivative, equate to 0, compute the second derivative. That's with respect to univariate. In the case of multivariate, the first derivative becomes gradient, the second derivative becomes Hessian. How many of you know of Hessian? We'll do that. That's what I'm going to do. So I'm going to talk about the univariate calculus. So compute the partial of Jx with respect to Jz0. Compute the partial of Jx with respect to Jv. Equate this to 0. Equate this to 0. So you need to compute that. Everybody? Is the problem clear? Come on, guys. Nod your head. If I say problem, not many seem to like it. You should love. Why? Practice makes it perfect. So compute the derivative equate to 0. Compute the derivative equate to 0. Now, let's look at this. So who is the unknown? Z0 and V. This is the quadratic. Let me finish on the note. This is a quadratic function in Z0. This is a quadratic function in T. When you take the first derivative, it becomes a linear function. Are you with me? So you will get two linear equations and two unknowns. Linear simultaneous equation, solve for Z0 and V. The solution is the optimal solution. I'm going to call it Z0 and V star. This is the test for you. If you cannot solve this problem, data assimilation is going to be tough. If you can solve this problem, wow, data assimilation is going to be so easy. So this is how you are going to test yourself. All of you? That's right. But instead of doing that, I'm now going to introduce multivariate calculus. That's what I'm going to do now. You have a question?
No, I got my answer.
Good. Are you all with me? Everybody, please. I want each of you to do this. I'm not going to ask you, did you do this? Did you do this? I'm not going to ask you to come to the blackboard. But in 2 weeks, when you go home, wow, I learned. Now I know. All of me, please. I want you to that aha. I want you to have that aha moment every day, in every lecture, every minute of that lecture. And that's what learning is all about. Please do. If you have questions, tomorrow afternoon, there is the open hour. We can discuss any questions that you may have. Now, I'm going to formulate this as a matrix problem. If I were to use slides, I would have done 15 minutes ago. But with slides, I cannot be this interactive. I hope this is, you like the idea of this interaction. All of you? All right. Yeah.
So if we solve these two equations, we will get two simultaneous linear equation in...
Two unknowns, Z naught and V. And then you solve them.
Okay, okay. Already we know Z.
All the ZIs are known, all the TIs are known. With me? So the coefficient, so how will this equation be? I will tell you this equation. This will be alpha Z naught plus beta V is equal to F1, alpha 1 beta 1 F1, alpha 2 Z naught plus beta 2 V must be equal to F2. See, that's how this equation will come into. And how do you solve 2 by 2 linear equation? By Kramer's rule, by elimination. I want all of you to do that. You got to practice. You got to practice. With me? Everybody. So the whole question is alpha 1, beta 1, alpha 2, beta 2, F1, F2 will all be functions of ZTI and TI. That's it. I have solved all these things. I'm going to give you the slides. With me? But don't wait for the slide. You should be able to do it yourself. Now, I'm going to use the multivariate approach. So, what am I going to do? I'm going to rewrite this equation, the old equation that I had, in a matrix form. So ZT1 is equal to Z naught plus VT1, Z22 is equal to Z naught plus VT2, ZTM is equal to Z naught plus VTM. Now, do you agree that the model can be written in the matrix form like this? I am going to call this vector as Z. I'm going to call this matrix as H. I'm going to call that vector as X. This is X, we already know. So this is a M by 1 column vector. This is M by 2 matrix. This is 2 by 1. All of you? How many of you are with me? Because instead of doing one at a time, thank you, instead of doing one at a time, I want to kill all of them together. In order to be able to do that simultaneously, what do you need? You need vectors, matrices, you need linear algebra. All of you? You need optimization. You need multivariate calculus. You need linear algebra. Everybody. So how am I going to rewrite this? This can be rewritten as Z is equal to HX. That's my model. That's my model. All of you? That's a linear model with two unknowns. Linear model with two unknowns. Now I'm going to generalize this. Now can you imagine a problem where this is a M by 1 vector, this is the M by N matrix, this is the N by 1. So this becomes this when N is equal to 2. So instead of 2 parameters, I could visualize problem with M parameters. Do all of us see that, please? So how will that M parameter equation look like? The M parameter equation will look like this. Let me write in here. ZTI will be equal to, ZTI will be equal to, now let's look at this now. So what is this? This is Z1, Z2, ZM. This is the matrix, which is H11, H12, H1N, H21, H22, H2N. This is HM1, Hm2, Hmn, this is x1, x2, and xn. In this case, so I get that as a special case when all the first column is 1, all the second columns are T1, T2, T3. But I can think of a model like this. So this is called generalized linear model. This is the specific linear model. So I'm going to use a specific linear model to induce a generalized linear model. I want to be able to solve generalized linear model. Why? Data assimilation problems are multivariate, high-dimensional problems. The unknowns are in high dimension. So here, what is the unknown? Unknown x is an n dimension. There are m observation. So I want to be able to solve my model z is equal to h of x. So you remember, I talked about static deterministic problem. The static deterministic problem is to be able to solve z is equal to h of x. How many of you have an aha here? Problem formulation, basic ideas. Any questions?
So here basically X is operator only.
What then? X is the matrix. Now I'm not going to use the word operator unnecessarily. Okay? I don't need right now. I simply call it the matrix now. Look at this now. Z contains observation. H is the link between the observation and the unknown state. X is unknown state. So here I'm going to introduce some basic things now. This is called the model space. You remember vector space we talked about? This is called the observation space. Observation space is Rm. The model space is Rn. X belongs here. Z belongs here. H is a map that maps X to Z. So this is the vector space. That's a vector space. This is the m. This is the n dimension. This is m dimension. Observation space, model space. Observation is a m vector. It could be anywhere. The unknown x is in the space. It could be anywhere. H is the bridge between model space and the observation space. So I have information in the observation space. I want to be able to bring that information into the model space so that I can use the information to estimate x. So H is the bridge. Are you all with me? Come on, guys, keep nodding. I'm looking for this, I'm looking for this. Especially I'm looking for this. If you are this, you are with me. I want to help all of you. I don't want to leave anybody behind. That's the reason. I know I'm going a little slow. I want to go slow. Why? If I put the slides, I also want to tell you something. It takes about half an hour for me to prepare a slide, but I cover it in 2 minutes. Are you with me? Come on, guys. So slides are good for seminars. Blackboard is still the best solution for a class. So model space, observation space, the link between the model space and observation space. Observation contains information. I want to be able to bring that information from the observation space to the model space. And that's what's being done by my JFX. So in this case, what is JFX? So I'm now going to define a error vector. So to do that, before I do that, I simply call it error vector EFX. EFX is equal to Z minus HFX. That's exactly what I did. This is the M vector. This product is a M vector. Matrix times a vector. How many of you know how to multiply matrix times vector? Come on, guys. Where are you? Where did you go to school? Did you not see matrix algebra where you had to multiply matrix with a vector? A lot of you are nodding their head but didn't raise your hand. Let me ask you once again. How many of you know how to multiply vectors and matrices. That's right. You have to raise this way. All of you? I want you to assume, every lecture has to assume certain fundamentals. Are you with me? I am going to assume basic fundamentals that is covered in a standard course at the MSc level, at the engineering level in India. Yeah, I went to school, remember, don't forget that. I'm a product like you. Kindergarten to PhD, I did everything in India. Going back once again, how many of you know how to do matrix vector multiplication? I'm interested in those who do not raise their hands. Where are you guys from? I'm just asking. Don't mistake me if you remember that? You know that, or you?
No, I didn't remember.
You did not take linear algebra.
I take, but I forgot.
Oh, good. That's right. How about you? You guys were the last to raise the hands. I'm not trying to put you on the spot. Please understand, I want to help you. You go to the doctor's office, right? You want the doctor to help you. If you go to the doctor's office and simply say, doctor, give me medicine, doctor, give me medicine, doctor, give me medicine, he'll slap you in your face and then he'll say, leave my office. You have to start talking. Doctor, I went to Italian restaurant yesterday night. I binged on the food. I had a couple of beers. I'm not feeling very well. Please help me to get out of this. You have to tell him the problem. He will solve the problem. Are you with me, please? So class is like a doctor's office. The teacher is like your doctor. You have to tell him the problem to help you to solve it. That's exactly what I'm doing. Nothing more, nothing less. Are you with me? So how many of you now know how to multiply matrices and vectors? You may know, but you have forgotten. Well, some of these things we can probably take care tomorrow evening. Are you with me? Please come tomorrow afternoon. There we will talk about these questions and the things at that time. With me? Don't mistake, I'm just trying to find out to what level I should go, where I can stop, and so on. So, look at this now. Z is known, H is known. I don't know X. So the error is function of a vector. This error is a M1. This is M by 1 vector. This is M by N matrix. This is N by 1 matrix. With me? And that's exactly what I had. That's a vector. What's the only difference? Here I had 2 parameters. There are N parameters. So this is called a linear model with 2 unknowns. This is called a multivariate linear model. So the multivariate linear model, I have model space, I have the observation space. H is the bridge between the model space and the observation space. H helps you to bring the information from the observation space to the model space. That information is expressed in the form of an error. Now I'm going to compute my J function, J of C. This is the vector. I want to be able to create a scalar out of a vector. E is a vector. I know how to handle scalars, but I don't know how to handle vectors very well, because this vector may have positive and negative components. What is the operation in linear algebra that helps you to convert a vector into a scalar? Inner product. Are you all with me now? You have to have an aha here. Come on, guys. Show some enjoyment. Aha. So I convert a vector into a scalar using inner product. So what is that inner product? That's equal to E of x times E of x. And that is equal to E of x transpose E of x. And that is equal to E of x square of the norm with respect to 2. All of you with me? So that is the sum of squared errors. The sum of squared errors is a function of x. Now, do you see inner product comes naturally? Do you see the square of the two norm comes naturally? Do we see the inner product and the norms are related to each other? Come on, guys. Now, do you see how linear algebra penetrates the analysis? So what's the problem? The problem is minimize j of x with respect to x when x belongs to Rn. This is an example of an unconstrained minimum in Rn. Multivariate minimization. I did not go directly. I built it from ground up. This is something you do. Where else you do this? I want to tell you the place where you have already done this. If you have not done this, you would not have gotten a master's degree. So I'm now going to go back. Can I erase this part now? Everybody please? So I'm going to a simple problem that you may have already done. You do an experiment in the laboratory. So that is a model. You give xi, I get yi. I want to be able to estimate what that model is, box is. Let's assume xi is in yi's. I want to uncover the relation. So this is y1, I'm sorry, x1, y1, x2, y2, xm, ym. So you conduct an experiment, you get this table. Then what do? You come to the, you close the lab, come to your workplace. This is x, this is y. X is the input, independent variable. Y is the output, is a dependent variable. You are going to plot. This is one point, this is another point, this is another point. I'm going to get a set of m points. This is called scatter diagram. If the scatter diagram looks like this, then you believe the box must probably a linear function. If the scatter diagram is like this, I can erase this part. If the scatter diagram, on the other hand, looks like this, then you probably believe it is y is equal to x squared, or y is equal to e to the x. If the scatter diagram is like this, then it's probably log of x. This is probably e to the x. Or it is probably x squared. So what is that you do? You conduct experiments. You bring the data. It's a univariate experiment, one input variable, one output variable. You plot the variable in the scatter plot. You look at the plot. Then you see, gee, it looks like y depends on x linearly. Y depends on x logarithmically. Y depends on x exponentially. Y depends on x quadratically. That guess you have to make. No one is going to help you. Once you make that guess, then what is that you do? You concoct a model. What is the model? Y is equal to a plus e to the power of b of x. R is equal to a times e to the power of b of x. A times log of x plus b. Or y is equal to mx plus c. So these are the class of models. These models that come from scatter diagram, in my model, this is the model. Why? I already start with a linear problem, where I know the unknowns and the knowns are collected linearly because of my basic physics, the distance traveled. Are you all with me, please? That's right. So in a physics-based problem, the model suggests itself. In a non-physics-based problem, you have to guess the model by looking at the scatter diagram. No one is going to give you anything in the silver platter. You got to earn everything. So you first need to conduct an experiment. At the University of Oklahoma, where I have been teaching, I teach a two-level system of course. First course, 3 credits, second course, 3 credits. I finished my entire book using 1-year course. A civil engineering student took my course, and he was interested in the following project. He's a transportation department person. The transport in the United States, east to west is 3,500 miles. North-south is about 2,500 miles. There are roads. It's one of the most beautiful road system in the world, and India is catching up. India has become very, very good in road system. To pave 1 mile of that road, in the 1960s, it used to cost $3 million. The concrete wears because trucks go. So they wanted to be able to find the composition of the concrete that will be less resistant to wear and tear. So he wanted to conduct an experiment. At the laboratory, they have measurements. He was a student from Bangladesh. He worked in the laboratory for 2 years. He collected a ton of data. He took a course. We suggested a nonlinear model. It worked very well. So what are the input variables? The speed of the car, the quality of the tires, the properties of the concrete, whether it is a hot sun or a cold snow. All of it, me? So you have to subject in the laboratory all these external conditions. So he has to have different concrete blocks, different makes of tires, different way to spin the wheel, different way to control the temperature. Can you imagine how many variables are there? Can you imagine how many times he has to conduct the experiment? He conducted that experiment and created this table. All of you? So he did a multivariate nonlinear model fitting to the experimental data simulation. All of you? Come on, guys. Is the problem formulation clear? Where the linearity comes from? 1 second. Where the linearity comes from? Who makes it linear? Who makes it nonlinear? How many parameters are there? Everything depends on the problem. Ultimately, what is the stopping point? I have model, I have data, I have model space, I have the observation space. I have to have the error. I have to sum the square of the error. X is the variable. I have to minimize this objective function, cost function, the criterion function with respect to X, where X can lie anywhere in the n-dimensional space. Unconstrained minimization. Hey, I'm done. This story is repeated in data simulation. Model after model, problem after problem, data after data. Are you with me? That's it. Yes, sir. Now I want to be loud so that all of them then carry your question.
Please explain this time.
Which you explain this one? This is the X. Here? Okay, good. What is the definition of inner product? X transpose Y. Look at the smile. You didn't see him. I see him. How do you define inner product, guys? This is simply a notation. And how do I compute this? That's right. And inner product of X with itself? Square of the 2 norm of the length of the vector. That's inner product. Are you with me? Good. Any questions on the formulation? So what's the homework problem? I want all of you to be able to solve the 2-variable problem. That's a homework. It is in your own interest, you must do this. You must try to get a 2 linear equation, solve this linear equation, get an optimal expression for Z naught and V star. This everyone should be able to do. Everyone should be able to do. With me? So what are the directions to move on? I can talk about optimization. So I'm now going to talk about optimization and bring the multivariate calculus into play to see how optimization and multivariate calculus combine themselves to solve this problem. How much time we have? Half an hour. Yeah. Are we making progress? Are we having aha? Wow. Good. Hey. It's good to have ahas, right? To a musician, he likes to see, if everybody in a concert looks like this, he'll say, oh, go to hell, I don't want your money. He'll go back, right? Cricket team plays. If there's nobody to cheer them, they won't play the cricket, right? Come on, guys. Your mom cooks. If you don't tell mommy, Mom, you are cooking very well, it's great, I enjoyed your cuisine this afternoon, Mom will stop cooking for you. Everything needs appreciation. Are you with me? That's right. That's right. I don't need appreciation, but you need to appreciate that you got it. Good. So now I'm turning the page now. So you saw the interaction between the problem formulation and linear algebra. Now I'm going to bring in the optimization theory and multivariate calculus. That's what the next step is all about. So with your permission, I can erase all these. So let's try to talk about minimization. So J of x is equal to, but I already know E of x is equal to z minus h of x. So if I substitute this in here, J of x now becomes z minus h of x transpose becomes z minus h of x. Are you all with me? How many are with me? Now what happens? Matrix algebra comes into play. So I need to talk about the transpose. So I'm going to talk about the properties of matrix algebra. Now, A plus B transpose is equal to A transpose plus B transpose. AB transpose is equal to B transpose A transpose. This is what you learn in linear algebra. This is what I would have given. Please understand, the linear algebra slide, I have a slide from 35 pages. If I want to expand all the 35 pages, it's a one semester course. So first you need to know what it is. You need to be able to understand what it is. Then you need to understand the proof of why it is true. So what is that? The transpose of the sum is the sum of the transposes. The transpose of the product is the product of the transposes taken in the reverse order. Where do these things come from? I don't make it, linear algebra makes it. Are you all with me? Now do you see the reason why I told you you need to buy a good book in linear algebra, have it with you? You are all doing PhDs. You are all asked to read papers by your supervisor. But how many times you have had difficulty in reading papers? It's everyday difficulty. Even after 50 years, I have difficulty. Everybody has a difficulty. So what is it you need to do? I don't know how the author got this. I had to go back. I got to go back. You can't stop there, right? Time keeps moving. You are getting older and older. You got to get your PhD soon. That's why I tell you, you have to get one book on every topic and build your own library. Please do. Spend 1,000 rupees. Your library will be pretty good. Spend 2,000 rupees. Your library will be pretty good. There are very many good books in India. Very cheap too. With me? So I want you to get a linear algebra book. So what is it you should do? For 1 week, 2 hours a day, I'm going to read linear algebra. For 1 week, 2 hours a day, I'm going to read multivariate calculus. 1 week, 2 hours a day, I'm going to read optimization. You need to build. All of it, me? That's right. PhD is essentially a self-imposed imprisonment, and you have to get out of it. All of you? That's right. That's right. So I'm going to use these in here. So this is equal to Z transpose minus HX transpose times Z minus HFX. This is equal to Z transpose minus X transpose H transpose times Z minus HFX. So I applied the first rule here, I applied the second rule here. Sum of the transpose is the sum, the transpose is the product. So this is like A plus B times C plus D. If I multiply, that will be 4 terms. How many of you are with me? Come on, guys. You look already tired, I don't know why. Coffee is coming soon, but please. Okay, this is equal to Z transpose Z minus Z transpose HFX minus X transpose H transpose Z plus X transpose H transpose HFX. 4 terms. All of it, me? Now, I'm going to show these 2 terms are the same. Now, let's look at this now. Z transpose HFX. What is Z transpose? That's a row, that's a matrix, that's a column. So this is a scalar. What does a scalar means? A number. There's a difference between a number and a vector. There's a difference between a vector and a matrix. A number is also called scalar. It's a real scalar. What is the property of scalar? Number 3. What is 3 transpose? It's 3. The transpose of a scalar is itself. If alpha is a real number, transpose of alpha is alpha. And this is a scalar. So according to that rule, this is equal to its own transpose. But the transpose of the product is a product of the transpose is taken in the reverse order. So there is another rule. What is another rule? Z transpose. Transpose is equal to Z. Reciprocal of a reciprocal. Inverse of an inverse. The transpose of a transpose is itself. Everybody, please. So this is equal to X transpose H transpose Z, which is exactly this term. Everybody? Therefore, without loss of generality, I can assume this is equal to Z transpose Z minus 2 times X Z transpose HFX plus X transpose H transpose HFX. All of it, me? Now do you see I'm teaching linear algebra along with that? If I told all these rules as a linear algebra, you will forget even before I finish telling. Now I'm trying to teach them in the context of a particular use. So these are the rules from linear algebra I have used. Now, this is with respect to X, this is a constant. This is the linear function. This is a quadratic function. Quadratic means what? Second degree. It's a quadratic function in the components of the unknown vector X. X has the n components. You remember I talked about a quadratic function in 2 unknowns yesterday afternoon? How many of you remember that? That's right. That's right. So these are the rules from linear algebra. This is my. So what do I want to do? I want to minimize. The minimum of this is what? To compute the minimum, now I have to go back to multivariate calculus. So I'm going to talk about the rules of multivariate calculus before I complete this problem. Everybody please. So you develop, You put it on hold, go back and perk up what you want, come back, push it forward, go back, learn, come back, push it forward. That's how research is done. I want to tell you a story. It's a true story about Einstein. In America, there is a channel called public television. They talk about movies. They talk about lives and works of very many great people. That's a beautiful 60 minutes movie on Ramanujan. One of the best movies on the life of Ramanujan. Even before the Ramanujan movie came here, they did it some 35 years ago in the USA. They have a 2-hour movie on Einstein. So Einstein was a young man struggling. He has ideas about relativity. He knew he needs tensor calculus. He had a classmate who did mathematics, but Einstein did physics. So he stopped all his work and went to spend 2 months with his mathematician friend, learned the tools of tensor analysis, came back, completed the paper. First theory of relativity. Why am I telling this? Even for Einstein, he had difficulty, he had to stop, he has to go back and learn. So if you and I have difficulty, are you with me? So difficulty, so don't tell anybody you have difficulty, everybody has difficulty. The challenge is how do you manage your difficulty? How quickly you manage your difficulty. Are you with me? That's right, that's right. So, what do I need now? This is the linear algebra. Now I'm going to do the parts from multivariate calculus. So let f be a function from Rn to R. So I'm talking about a general form. I want to develop the theory of multivariate calculus before I come back here. I put it on hold. What is that I need to do to be able to minimize? What do I fall back? I fall back on multivariate calculus. So what multivariate calculus tells you? So look at this now. There are f from R to R, f from Rn to R. I hope you all understand the notation of this. This is R, f is this is f of x. So in here, this is Rn, this is R, this is x, this is f of x, this is x belongs to a vector. So what is this called? This is called scalar valued function of a vector. You remember I talked about functional yesterday? It's a functional. What is this? This is a scalar valued function of a scalar. There's a third class of function we will use, but a little later. So in this world, to minimize, what do I do? df by dx must be equal to 0. d square f by dx square must be positive. These are the two conditions. Are you all with me? That is done in calculus. I did my BSc physics with ancillary mathematics. The ancillary mathematics, they did this. With me? Come on, guys. Now, in here, what is the analog of that? The gradient of j of x must be 0. The Hessian of j of x must be symmetric and positive definite. positive. Symmetric and positive definite. It's the matrix. So this is the n by 1 vector. This is the n by n matrix. This is the vector of first derivative. This is the matrix of second derivatives. So I'm going to talk about that first before I come here. Now, do you see this problem is exactly the same as this problem? Hello? How many of you are me? Some people raise the hand like this. So you're halfway through, right? No, you have to be full way through. You have to be full like this. Come on, guys. I want to tell you, if I know how to solve this, I know this, but that is basic. This is applied. Are you all with me? Am I making your life easy? How many of you say I'm making your life easy? How many of you having aha? You don't show it. Why don't you show me? Smile, nod. Wow, aha. That's right. Please enjoy life and show I enjoy life. Are you with me? It should be no secret that you enjoy life. Good. So what is gradient? The gradient of f. So I talk about general. I can probably change this to f. So here I want to talk about general. The f becomes j. When f is j, that becomes that. So here is f. F is generic. So what is gradient of f? Partial of f with respect to x1, partial of f with respect to x2, partial of f with respect to xn. The vector.
How this
Which one?
second gradient becomes n by n?
This is the matrix of second derivative. What is the question?
How this becomes n by n matrix?
Yeah, that's what I'm going to show you. That's what I'm trying to tell you here. So let's assume, for the sake of illustration, let n be 2. In that case, x is equal to n, x1, x2. With me? So what is the gradient of that? That is equal to that's the Hessian when n is equal to 2. So when n is, for a general n, what will be this? This will be a n by n matrix. This is a 2 by 2 matrix. What is that n by n matrix? That n by n matrix I can simply talk about like this. Del square f by del xi del xj. This is the n by n matrix. 1 less than I less than n, 1 less than j less than n. Got it, sir? Hessian. So what's the question he asked? What is the definition of Hessian? What is the definition of a gradient? Are you all with me? Who teaches you? The data assimilation guys don't teach you. The mathematics guys should have taught you before you come to data assimilation. And which part of mathematics? Multivariate calculus. In general, in none of the universities, they have a course in multivariate calculus unless you do mathematics. Are you with me? That's right. Even MSc Physics, they don't do multivariate calculus too much. They do some. They do some. They do some. All of you? So even though you may have gotten masters in mathematics or masters in physics, there are many things that you need in data assimilation that you may not have had an opportunity to see earlier. That's what I'm trying to fill in. You have to ask yourself the question, why are you here? Bangalore is a good place, but it's too hot. It used to be much better. Somebody gives you free boarding, lodging, this. Is that the reason? No, you came here to learn. All of you with me, please? Learning is the bottom line. If that doesn't happen, it is not worth the exercise. It's not worth the exercise. All of you? Now, do you know how to calculate the gradient? Do you know how to calculate the Hessian? Do you understand the gradient is a vector? You understand the Hessian is a matrix? This matrix is a symmetric matrix. Why this is symmetry? From basic calculus, you should know the second mixed partial derivatives are the same. If I find the derivative of f with respect to x1 and then x2 and x1, they are the same. So this matrix is naturally symmetric. Tomorrow afternoon, I plan to work on a problem where we'll compute all these things. All of you? Just to be able to guide you. Just to be able to guide you. Now, there is another term. So I understand what is symmetric. A symmetric matrix is A transpose is A. The elements above the diagonal are mirror image of the element below the diagonal. The definition is A transpose A. What is positive definite? That's a very technical term. One way to understand the positive definiteness is as follows. I'm going to define positive definiteness much more formally later. How many of you understand, have heard of eigenvalues of matrices? Good. It's very easy to teach to you then. If all eigenvalues of a real symmetric matrix are all positive, then the matrix is positive definite. That's a test. So positive definiteness is a property. The way to test for positive definiteness is to compute all the eigenvalues. If all the eigenvalues of a given symmetric matrix are all positive, then that matrix is called symmetric and positive definite matrix. And for short, we simply say SPD matrix. All of you? I'm teaching matrix theory, I'm teaching linear algebra, I'm teaching multivariate calculus. I'm not teaching them for the sake of this, but I'm doing it in the context of that. Why do we do this? Because this is a problem in multivariate optimization, multivariate minimization. So what is the next best thing to do? I have to compute. What time we stop? I'm not that I want to stop, but 11. Okay, good. Hey, he's the boss. He says stop, I stop. He says continue, I continue. He's a good friend. Now, do you see the relation between that piece? This is essentially F, but it's made up of 3 components. So what are the other rules you have? The other rules of multivariate calculus are as follows. The gradient of F plus G is equal to the gradient of F plus gradient of G. The Hessian of F plus G and the name for this is called Hessian. This is called gradient. Gradient vector, Hessian matrix. Hessian matrix is naturally symmetric. Not every symmetric matrix needs to be positive definite. Positive definite is an additional condition. For a symmetric matrix to be positive definite, the eigenvalues must be positive. I'm assuming I know how to compute the eigenvalues and have tested it is positive. So what is positive for numbers is positive definite for matrices. I want to talk about that for a moment now. So how do mathematicians develop mathematics? They see a result in real analysis. They want to find out is there an analog in vector analysis. They see a result in vector analysis, then they want to find out is there an analog in matrix analysis. That is me. So they would like to be able to understand what properties hold good in what system. For example, in numbers, can I erase this part now? Good, we have done with that. I hope you have taken notes on that. In numbers, AB is BA. In matrices, AB is not equal to BA. If AB is equal to BA, means what? It is commutative. It is not commutative. So matrix algebra is a non-commutative algebra. Real algebra is a commutative algebra. In vector algebra, it's a commutative, with respect to inner product is commutative. How many of you have done vector analysis in physics? Dot product, cross product. You remember a cross product of two vectors? A cross B is not the same as B cross A. How many of you know that? That's right. So cross product is not commutative. Dot product is commutative. Matrix product is not commutative. Real product is commutative. To understand the differences between the mathematical system is one of the underlying educational challenges. Are you all with me? That's right. So commutative, non-commutative, positive definite, the sum rule, the sum rule. So with that, I'm now going to come in here. So the gradient of J, with respect to X, there is nothing here, 0. Because that's independent of X. Now, I need to be able to compute the gradient of this. I need to be able to compute the gradient of that. I'm going to show you how to do that by another property. So I'm done with this. Let this be here. So let it be here. Let me erase this. So what is the first term? The first term is a linear term in X. I need to compute the gradient of that. So what am I going to go back to? I'm going to go back to multivariate calculus. So sometime I go to matrix theory, sometime I go to vector theory, sometime I go to multivariate calculus. You need to know which one I need to pull in. All of you? That's right. Hey, how many of you know cooking? How many of you cook? I'm a decent cook, I can survive. In cooking, there's an order in which, right? You cannot put salt before you cook the vegetable because vegetable may not cook well. If you talk to two different cooks, they will fool you, right? Don't do this, do this, don't do this, do this. But if you start cooking, then you know you can become a cook yourself. Then you can mix and manage. So at what time, what to do is what we are after. So here I'm now going to talk about this. So let's talk about your general function f of x. Let this be equal to A transpose x. So A is a vector, x is a vector, it is a linear function of x. Everybody please. Are you with me? I want to be able to compute the gradient of this. Why? This is a linear function of x. This is also a linear function of x. Everybody plays. So to be able to handle this, I need to know how to handle that. What is this? It's a quadratic function of x. I need to know how to handle the quadratic function of x. How many of you are with me? That's right. So what is a typical model in calculus they will use for a linear function? A transpose x, where A is a constant vector. So what is this? This is summation AI xi. Therefore, what is del of xi is equal to AI. So what is the gradient? The gradient of f is equal to f by x1, f by x2, by xn, which is equal to a1, a2, an, which is equal to a. So I got the first formula for multivariate calculus. The gradient of f is equal to a if f is equal to A transpose x. In differential calculus, what is the first formula you do? Differential equal to x squared is 2x. X to the n is the n times x to the n minus 1. Are you with me? So the first formula of a multivariate calculus is this. How many of you are with me? Now I'm going to do, let f of x be x transpose ax. Why am I doing this? I want, this is the quadratic function. What is the model of a quadratic function? X transpose ax. So I'm going to assume A is symmetric. Why symmetric? We will talk about it later. A is symmetric. So let us also assume x is equal to, n is equal to 2. I want to be able to illustrate this. This is x1, x2, a, b, b, c, x1, x2. So A is this matrix, x transpose x, and that is equal to A times x1 square plus 2b times x1, x2 plus c times x2 square. All of it with me? Now I need to be able to compute the gradient of this. What is the gradient of f? The gradient of f is equal to the gradient of f with respect to x1, the gradient of f with respect to x2. What is this? This is equal to 2ax1 plus 2bx2. This is equal to 2bx1 plus 2cx2. That's equal to 2 times ab bc times x1, x2. That's equal to 2ax. So I get the second formula. If f is equal to x transpose ax, gradient of f is equal to 2ax. So this is the first formula. This is the second formula. Are you all with me? That's right. Now let's come here. I want to be able to rewrite this as A transpose X. So look, 2, I don't have to worry about it, right? A constant always comes out of the derivative. So Z transpose X, let it be A transpose X. So what will that be? This implies Z transpose H is equal to A transpose. So Z transpose H transpose is equal to A transpose is equal to A. Therefore, A is equal to H transpose Z. How many of you with me? That's a linear function. I do know how to compute the derivative of A transpose X, but this is not in the form of A transpose X. I want to be able to convert this into the function that I already know. So I'm going to rewrite this as A transpose X. This will be equal to A transpose X if this is A transpose. I take the transpose of both sides. A. The transpose of the product of the transpose is taken in the reverse order. The rule that I have already talked about. So A is equal to H transpose Z. So if I change the variable by substituting H transpose Z is equal to A, this becomes A transpose that. Therefore, the gradient of this term must be equal to A, which is equal to Z transpose, I'm sorry, H transpose Z. Boom. Are you all with me? How many of you are with me? That's right. Therefore, I can fill this term to be 2 times H transpose Z plus. Your silence is deafening. Are you have any questions on that? Okay, good. Now let's rewrite this term. X transpose H transpose HFX is equal to X transpose AFX, where A will be equal to H transpose H. A H transpose H. So what is A transpose? A transpose is equal to H transpose H transpose. The product of the transpose is taken in the reverse order. This is H transpose H. That is equal to A. So A transpose is A when A is this. A is symmetric. Yeah. Are you with me? Just 2 minutes. I know, the coffee is waiting for us. So what is the gradient of this? 2ax, but a is this. So this is going to be 2 times h transpose h of x. The whole thing must be equal to 0. All of you with me? We have been together for 1.5 hours. We have covered a lot of grounds in linear algebra. We have covered a lot of ground in multivariate calculus. We have covered a lot more grounds in data assimilation, assimilating data into static models. Are you all with me? We will break, we will convene at 11:30, and we will have one more session. There we will be able to solve this and compute the optimal solution x. I'm not done until I compute the optimal solution. Are you with me, please? That's right. Any questions? Let's take a break. Thank you.
We'll break for tea now. 11:30 we will assemble back.